Welcome to the lectures on evolution of air interface towards 5G. So, currently we are reviewing the minimum requirements for IMT 2020 or 5G, and in the previous lecture we were seeing some of the requirements. So, here we continue on that. So, as was briefly mentioned, that energy efficiency is an important metric which we should be taking care of, and in that efficient data transmission in loaded case is something which we should look at, as well as low energy consumption when there is no data. So, these are the two different aspects which are to be looked at, and we will try to look at some of these in the later part of the course. Reliability is in the range of 1 minus 10 to the power of minus 5 success probability. That's very huge success probability for layer 2 PDU of 32 bytes within 1 millisecond in channel quality of coverage edge for the urban macro URLCC test environment, assuming small application data. So, basically it talks about a huge success probability when you talk of reliability, packet delivery probability, that means with a very large number of packets, most of it is successfully delivered within the channel conditions of the test environment as would be specified. So, this ultra reliable low latency communication test scenario which is of interest, under this condition a very high success probability is required. Due to low latency, a very low latency has to be satisfied, and there is a certain packet size which is to be specified, and probably a larger packet size would be also okay, but one has to check with the latency requirements. So, such requirements are usually with respect to control and command applications. So, then large packet size is generally not the situation in that case, which has to be delivered within a short delay. So, moving beyond, this was one of the last things that we were seeing in the previous lecture. So, here mobility has been specified in multiple classes like stationary, pedestrian, vehicular and high speed vehicular. So, there are different range of velocity. Stationary is of course 0 kilometers per hour, pedestrian is like walking, vehicular is with traffic, with cars and other things moving around in city and urban area, semi-urban area, whereas high speed vehicular is kind of moving on highways and high speed trains. So, speeds up to 500 kilometers per hour have to be supported. So, what this essentially means is that this influences Doppler, and further when we have higher and higher frequency bands, the cumulative effect becomes terrific. So, that has to be addressed in some of the solutions. So, the traffic channel link data rates normalized by bandwidth have been specified with different mobility conditions. So, what is it saying? Like under indoor conditions, one has to take the pedestrian, and the normalized traffic channel link data rate, that is bits per second per hertz, is 1.5, whereas in rural the mobility is 120 and 500 kilometers per hour. Two different cases have been given, and the spectral efficiency or bits per second per hertz is given by these numbers. So, what we essentially see is that as your mobility increases, the spectral efficiency decreases for all reasons of communication and channel properties that keep on getting worse and worse when higher and higher mobility comes into play. So, what it also says that it should support bandwidth of 1 gigahertz above 6 gigahertz. So, when you talk about millimeter wave band, this becomes 1 gigahertz bandwidth is required to be supported when we give the specification of bandwidth, and at least 100 megahertz have to be supported in the other bands, that means the sub 6 gigahertz. So, if you go to higher spectrum and we add mobility to that, it becomes a terrible situation to address. So, what we summarize now all our discussion till date as what we could see is that there are diverse deployment scenarios. We have seen at least 3 different deployment conditions. There is diverse spectrum. We have clearly seen here that one is below the sub 6 gigahertz and the other is above 6 gigahertz, which is usually in the millimeter band, and when you go to the 30 gigahertz or 50 gigahertz or 60 gigahertz band of spectrum, the propagation characteristics are different, the device characteristics are different. So, this spectrum actually makes a lot of impact on the system design, as well as not only is your device getting influenced, but the available bandwidth is different, and since the bandwidth is different, therefore, again you have lot of opportunity to play around with the design of the system. So the spectrum is not a single spectrum, nor is it uniform. It's kind of quite different, which is to be present. And there would be variety of services and variety of devices like machine type communication, smartphones, and all things would be present. So what we are seeing is that by one single technology, one is required to serve different deployment scenarios, different spectrum, and different devices and services, and this gives birth to the new radio, also referred to as the NR. So thereon we will start looking at some of the new aspects which have been introduced, but we will lay our foundation strong by revisiting the things which have happened earlier, because what things are going to come in future have their foundation on what has happened in the past. So we'll kind of go back and forth in building the foundation as well as looking into the future technologies. So in this particular screen, or in this particular slide, we have more or less summarized some of the important aspects or some of the notable contents which come as part of air interface for the next generation. So self-organizing networks have been there, and they will still remain very critical for the 5th generation system. One very important thing that has come up is scalable OFDM numerology, which is part of the new radio, which we will discuss. Multi-user massive MIMO, sometimes this is an extra word put along with massive MIMO, but this clarifies the entire details. This is also an important part of the 5th generation system. LDPC coding has already been there. There are more error correction codes which are potentially capable of providing the necessary benefits that are required. Low latency slot structure design. So basically to support the low latency, one has to redesign the frame structure, which is otherwise not supporting low latency. That means, if we look back at the LTE advanced or the 4th generation system, it is not capable of supporting a very low latency of 1 millisecond as desired in this. Adaptive beamforming and beam tracking, especially in case of millimeter wave, is also very important. So we will get some time to look into these aspects. Non-orthogonal multiple access, data offloading into heterogeneous networks. So these are some of the important modifications or enhancements or improvement in the radio access network or overall radio access technology, which drive the future generation or the 5th generation mobile communication systems. So with this, we more or less close our discussion on the understanding of how the requirements come up and how things have changed from previous generation, right from 2nd generation to 5th generation. With one of the important motives is to understand or to kind of train ourselves and kind of predict the future, that what is expected or how things are going to grow, because we have seen this industry for quite many decades now. And the other aspect is also to highlight how the numbers have changed and what new requirements have come in, as well as the deployment scenarios are becoming different. So I mean, overall there is an entire growth in all possible dimensions. If you look back in what we have discussed, some of the early generation systems had only few parameters and only countable objectives to meet. Whereas in the newest generation of technologies, the number of parameters to be observed or measured has increased phenomenally, as well as the requirements have also grown many folds. And if you check back with the amount of data that's expected to be flowing around in these networks, it's I mean it's beyond our normal imagination. It's a huge amount of data. And what is the outcome of such things is that we have been able to get new technologies, new solutions. So there was a challenge, and the challenge has been met quite successfully, and a lot of development has happened in the technology front, which we hope is only going to help us help the society evolve into a better human society and more safer and probably a much superior being in the future. So with this, we continue on this particular lecture, and we look at some other aspects that are necessary as part of the curriculum. Yes, so we continue with the next lecture. So in the next part of what we had to cover, somehow we were not well synchronized with the timelines for each of the lecture slot, but that does not matter, we will continue. So far we have seen the requirements and the specifications. We have also seen the requirements for the 5th generation, and now we are supposed to look into the solutions for the 5th generation. But however, I thought it pertinent that we look back at some of the older solutions and some of the foundations. Now, the reason is that if we are supposed to begin with the study of waveforms. Now, when we look at the waveforms for the 5th generation, we can get a jump start and get into things, but we also have said that we also want to look at some of the front runners in the waveform technology that were in the contention towards being a air interface. Here it is important to note that how things have evolved over time. When the 2nd generation came in, there was the TDMA FDMA approach, or the GMSK, which was the fundamental waveform. At that time, the spread spectrum communication was also well known and it was also being discussed, but however, with consensus people chose to remain with TDMA FDMA, and they came up with GMSK. They rejected the spread spectrum method of communication, which could provide us the CDMA technology. When the 3rd generation solutions were being discussed, then the multi-carrier or OFDM based technology was already available. Now, at that time, spread spectrum or CDMA technology was a little bit more mature, and then if you look back into the waveforms for the 3rd generation, it was spread spectrum communication, it is rather CDMA communication, and it is also known as WCDMA, wideband CDMA. Whereas OFDM, although was pretty much available, was rejected as the candidate waveform. When we move forward and go into the 5th generation, what we find is that in the period of 2010 to 2015-16, there have been several candidate technologies which were in the foray, and they were like generalized frequency division multiplexing, filter bank multicarrier, UFMC, and many other windowed OFDM and many other proposals which have been there. However, what has been accepted is largely a variant of OFDM, which is a more scalable numerology structure of OFDM. So, what we see is that at every stage, some technologies which are new, which can contend with an existing technology or a more mature technology are proposed, they are well compared, and usually where there is more consensus, it is taken. So, it is very vital that we also look at the waveforms which were there and contending for the 5th generation candidate technology, because there is a high potential that one of them will become air interface for next generation, not simply by virtue of the progression of history, but these were being developed by a large number of people over a long period of time, because they had felt that OFDM has certain shortcomings which need to be addressed. So, over the next few years, it is further expected that these waveforms and these technologies are even improved beyond what they are available today. More things get added to them, so that they are more mature and they can probably replace the existing OFDM and overcome some of the shortcomings which OFDM has. Now, incidentally, some of the important waveforms in this category have their roots in the 2nd generation system, and some of them like filter bank multicarrier and others have a special property by which the out of band radiation, that means when the signal goes out into the air interface, then the amount of signal that leaks outside its bandwidth is much lesser in these schemes than in OFDM. And if we look back at what happened in the 2nd generation, that is the GMSK, It is one of the most bandwidth efficient signaling techniques. And when we look at some of the baseline structures, and if we study them, it will be easier and for us to study the filter bank multi-carrier and other setups, because it is built on the same platform. So, in order to set up the platform, we decided that let us look into the basics, and through which we will cover the earlier generation, as well as give us the premise and foundation for looking into the future generation systems which are yet to come in. So, with this we set up the basic signal model. The other intention for us to look into this basic signal model is that there would be many participants who have been working with a lot of advanced protocols and mechanisms, but when we talk about signals, we need to get back to the basic framework, the basic way of writing the expressions, so that we benefit end of the day by revisiting some of the original things, so that we get trained, and finally we are able to write the newer solutions by ourselves. So, for that we need to relook at the foundation. We will not really go into a lot of great details, but only the important foundation that is necessary to help us carry through the important parts of this particular course. So, with this, let us get into the basic signal model. So, typically when we communicate, the channel is usually band limited. I mean, that is kind of understood by all of us. We do not have infinite bandwidth to transmit a given signal, because the channel is split into smaller chunks, and each particular service is given one particular set of bandwidths. That is pretty well known to many people, and those who are new in this particular domain. Just take an example of GSM, where each of the carrier occupies 200 kilohertz, overall 1.25 megahertz kind of is given for communication. If you look at the fourth generation or the fifth generation, it's kind of overall 5 megahertz is given for any one communication band. So, it's always desired that the signal occupies a certain finite bandwidth, and hence we usually say that the channel is band limited. And of course, it is centered around the carrier frequency. So, there is a carrier frequency which is associated with the band, and when we talk about the sub 6 gigahertz, we also mention the center frequency. When we talk about the millimeter wave, we also mention the center frequency. So, the carrier frequency is kind of the center frequency. So, signals and systems and channels are usually narrow band. I mean, so we are talking about narrow band systems. In narrow band systems, the bandwidth of the system should be much less than the center frequency. So, our rule of thumb could be 10%, but usually it is even smaller than that. So, we are generally going into the realm of narrowband systems. That is something we should remember. The transmitter generates a band pass signal. That is again something many probably young students would also be participating in this particular course, and our intention is to set things proper. So, just to get things in place, the band pass signal is essentially the signal which has a certain band centered around a carrier, and the carrier is not 0. All right. So, that is what is meant by band pass, and when the carrier is 0 and you have your signal which is spanning around the 0. So, it is usually the baseband or the low pass signal. That is what is referred to. We will see them in the model. So, usually it is convenient to represent in equivalent low pass form. So, this is what you usually study in digital communications. That is, when we are studying systems, we can create a signal which we can up convert to any frequency of our choice. At the receiver, we have to down convert the frequency and then do the baseband processing. So, what is very important is that we look at the baseband signal processing part or the baseband signal model part, because if it is only the carrier and we can choose any value of the carrier, then we should rather focus on the baseband part, and when necessary we can uplift the carrier to a particular center frequency and down convert it at the receiver. However, we will not put in this particular model, but we will see later on is that since the signal is band pass, it passes through a band pass channel. To analyze the overall effect, we should also have the equivalent low pass of the channel, and so that we can study the entire transmitter channel receiver in the equivalent low pass form. So, one of our objectives here is to start with this setup, so that all of us who are on board are able to handle this setup. I understand that many of you already know this, but I also believe that there would be some of us who would be benefited with this basic analysis. So, we consider ST as the signal which is real valued, and ST is narrow band and centered around the carrier frequency Fc. Okay. So, the aim is to get the mathematical expression of such a signal. That is what we are interested to do. So, we first construct a signal which contains only the positive frequencies is in NT. So, that is the first step towards getting that. So, that means your SF, which is the spectrum of ST, is having plus Fc and minus Fc, and signal is around Fc. Okay. So, the Fc is the carrier frequency, the signal is somewhere around Fc, and it can have a particular structure or the spectrum of occupancy. So, when we say that we want only the positive set of frequencies, that means we are interested in only these frequencies, and the other reason is that from this you can regenerate them. So, it is probably good enough to do with the positive set of frequencies. So, S plus of F, which the plus indicates the positive frequencies and SF indicates the spectrum of S of t, or is the Fourier transform of ST, is 2 UF times SF. So, where SF is the Fourier transform and UF is the unit step function in the frequency domain. So, that means you take only the right hand portion and you do not consider the left hand portion. So, yeah. So, that means as if we do not consider this, but since you have considered only half of them, because you have taken the unit step function, you multiply by 2, so that the total power or the total energy is conserved, right. So, that is why we have 2 UF SF in order to describe the signal which is in order to describe the signal which contains the positive frequencies. The equivalent time domain expression would be S plus of t, which is the inverse Fourier transform of SF or S plus of f. So, which is the inverse Fourier transform of S plus of f. If we look at it, it is basically these two things. So, it is a convolution of the inverse Fourier transform of 2 UF and that of SF. Now, we already know that the inverse Fourier transform of SF is ST, or SF is the Fourier transform of ST by definition. That is what we have over here, that is what is being given over here. So, therefore, it is a convolution of two time domain signals. The inverse Fourier transform of 2 U of f can be written as delta t, which is the delta function, plus j upon pi t. So, what we have is this entire function convolved with ST, this is ST. So, delta function convolved with ST is ST, and this particular is expression is something which we should look at. So, here we will define S hat of t as HT convolved with ST, where HT is defined as 1 upon pi t. So, you see that you have 1 upon pi t over here. So, if I define this as HT, then HT convolved with ST is defined as H hat of t. Okay. So, this HT, which is 1 by pi t, is usually known as the Hilbert transformer, right, which is a 90-degree phase shifter. So, S plus of t can be written as S of t plus j S hat of t, going by this expression. If you use this particular line in the previous, you get S plus of t as ST plus j S cap or S hat of t. So, this we have obtained as the inverse Fourier transform of S plus of f. So, essentially this is the time domain signal which contains the positive frequencies only. The equivalent low pass, that is SL of f. Okay. So, that means we want the equivalent low pass. From this, it is very easy that S plus f plus f c. That means, whatever is, if I put S L of 0, we get S plus of f c, correct. So, that means, this is down converting your S plus of f to S L, right. So, that means, it is removing the effect of f c, right. So, this is the low pass equivalent form. So, if I put f as the value which is just little bit positive, that means delta positive, this S L of f is basically S plus of f c plus the little bit. That means, in other words, it is nothing but this particular point. Okay. So, like that we can keep increasing values of f, and we can collect all the values of f over here and all the values of f over here. So, essentially speaking, S L of f would appear like this, centered around 0, all right. So, that is S L of f, and then we can get the S L t, that means the time domain representation, by simply getting from this, which is S plus of t by Fourier transform properties, e to the power of minus j 2 pi f c t, which is also representing a down conversion operation, and which is equivalent, I mean, this also is equivalent to the expression of down conversion which is done at the receiver. So, the frequency domain translation of frequency in time domain, it is simply the down conversion or multiplication by e to the power of j. So, this is by virtue of Fourier relationship. So, S L of t, that is what we have, is the low pass equivalent of the positive set of frequencies of the signal, or the signal containing only the positive frequencies, can now be written as S plus of t. We have obtained S plus of t, which is over here, that is S t plus j S cap of t, and we have the remaining term e to the power of minus j 2 pi f c t. So, what we have over here, in other words, we could also write that S t plus j S cap of t is S L t e to the power of j 2 pi f c t. So, that means, S L t is modulated, and here what we see, it is demodulated. So, this is like up conversion of the low pass equivalent form of the message, and this is the structure as it should be, and it is kind of a single sideband transmission that what you have studied earlier in analog communication systems and other courses. So, this is the baseline structure which some of you have already done, and those who still remember, it is a revision of those concepts, and those who have probably forgot, I mean, it is a good way to recapitulate some of the things. Okay. So, therefore, what we see is that S L is in general a complex nature. So, what we see over here, S L is having j and there is e to the power of minus j. So, in general, this is a complex in nature. So, if this is complex in nature, I could write S L of t as generically x t plus j y t, because this is of complex form which we have seen. So, I could say that let me write it in this form. So, then I have to connect what would be the relationship of x t with s t and y t with s t. So, we are saying that let this whole thing, quickly let me take this whole thing, let us write it as x t plus j y t, right. This is what we have mentioned. Yeah, and this is exactly what is written over here. So, if we replace this into the previous equation, what we are going to get is S t equals to x t cos 2 pi f c t minus y sin 2 pi f c t. So, this is also straightforward, because you can clearly see that you would be writing that x t plus j y t e to the power of minus j 2 pi f c t, and this you would expand as cos 2 pi f c t minus j sin 2 pi f c t. So, simply x t cos 2 pi f c t would come over there and y t sin 2 pi f c t would come over there. So, then you have to go back to the previous page and equate the different terms that is there. So, we have S L T with this, and we have said that S T is real valued. So, if you take the real valued part of this, then so basically we are going to have the other terms, which is j y t cos t and j x t sin t. So, the real value terms are x t cos 2 pi f c t and y t sin 2 pi f c t. So, this is the real value terms that you encounter with S t, and so this is what is the expression of S L t, right, and S cap of t is basically the other component, which is with the j component. So, what we have over here is essentially the S of t in the desired form as we require. So, what we get is there is the transmitted signal, there is a cosine carrier, there is a sine carrier which are quadrature in nature, and we have signal bearing forms, that is x t and y t, which is going to carry our signal. So, this is a basic structure on which we have to build upon for all possible future expressions, and I think it is very vital that we abide by this framework, so that all representations that we will do will fall into place. So, when we have S cap of t, we have already discussed this. So, you could also write S t, what we have done, as the real part of this particular thing, right, which we have actually done it over here. So, that is, we could say that it is S L t e to the power of j 2 pi f c t, right. So, when we say it is S L t e to the power of j 2 pi f c t, we could also say that let us write S L t, which is in general complex, as A t e to the power of j theta t. In general, we can write that. So, where A t is square root of x square t plus y square t and theta t is tan inverse y t. In that case, S t can be written as real part of this, already we have seen in the previous page, and A t e to the power of j 2 pi theta f c plus theta t. So, if you are taking the real part, A is real because it is the amplitude over here, cos 2 pi f c t plus theta t. So, this is the familiar form which we are generally used to when we are discussing signals, and this clearly brings out all possible ways of handling the particular signal, because here we have A t which you can modulate and you get amplitude modulation, you will modulate theta, you will get phase modulation, you also have access to carrier, that is and you get frequency modulation. So, we would like to stop the discussion of the signal model over here now, and in the upcoming next lecture we will carry on with this basic framework to develop the structures that were there earlier, as well as it will provide us the premise to look into the structures or the signal model that have been there in the IMT Advanced, as well as that are going to appear in IMT 2020. Thank you.